All right. So for number one, D was the incorrect one. This is not nitrite. Nitrite's NO2 minus. That's NO, nitric oxide, or nitrogen monoxide. Or as a ligand, we would call it nitrosyl. Or they might call it something else, nitrogen oxide. Choose the incorrect formula name combination for the ligands. Hydroxide is not O2 minus. Hydroxide's OH minus. So this A is incorrect. Which of the following could be a chelating agent? Chelating agent would have to donate two lone pairs from two different atoms. So ammonia is impossible. It's monodentate. Cyanide, no, not possible. Either the carbon or the nitrogen. And for cyanide, it's the carbon end. D looks like it could potentially, but what's the problem with D? Four-membered ring. It would be too strained. So this nitrogen and this nitrogen could donate potentially, but the four-membered ring that results would result in 90-degree bond angles for sp3, which is 109. So too much ring strain. B, there's only one donor atom on B, which is nitrogen over here. Everything else doesn't have any lone pairs. And so none of these is the correct answer. What is the correct charge for EDTA? That one was tetraacetate. Each acetate's -1. Ethylene diamine's neutral. And so if you have ethylene diamine tetraacetate, it's got to be -4 for each of the four combined acetates. What is the best coordination number for EDTA? This one, the best one is not poly. It would be probably hexa. It'd be more specific. So sometimes you get questions like this where both are correct. C and D are correct, but D would be better, the better answer. So you choose the best answer for this particular one. Formation of complexes involve Lewis acid base, which is electron pair donor and electron pair acceptor. So C, electron pair donation. It's a donation that results in sharing. But one atom donates both bonding electrons here. And so we form the special bond called the coordinate covalent bond or the dative bond, which is another question I've asked on multiple choice many times, but not this time. 7, how many chlorides for each of these? Well, chloride, that's an ion. And when we talk about coordinate covalent bonds, this chlorine is not an ion. This chlorine is coordinately covalently bound to the metal, and so it's not an ion. And so you wouldn't expect it to break off like an ion. And so 2 would be the answer because these two are just counterions. And so this is the triamine, chloro. This would be 4 coordinate cobalt, 3 chloride. And so 2 is the correct answer here. So this is when Werner won the Nobel Prize, and there's a question in the homework about conductivity. The conductivity is going to depend on the number of ions that you have in solution. So the more ions you have in solution, the higher the electrical conductivity. And so it depends on how many ions these species break up into. And this is very perplexing because this is actually one of the compounds that for Werner's Nobel Prize. Let me just talk about that briefly because he won the Nobel Prize for this. So if we have, let's close that. Pre-Werner, if you have cobalt 3+ and you have 3 chlorides, that's perfect because what we're going to make is cobalt 3 chloride, like this. This is a solid. And let's say there's some moisture in the air, H2O gas, like humid air. If you had dry air, there's no humidity and there's no water vapor in the air. But if you have water vapor, what happens is, what type of structure does cobalt 3 chloride adopt? Well, first I would ask myself, is it a ionic compound or a molecular compound? Ionic compound. Ionic compounds adopt what type of structure? Ionic compounds adopt what we call an ionic lattice. What does an ionic lattice look like? Okay, Rebecca, you have it? Yeah, just expanded. Yeah, exactly. That's it. And so what we have are cations and anions. What are bigger, cations or anions? What's bigger? Cations are bigger? Cations are losing electrons. As they're losing electrons, what happens is the number of protons doesn't change, and it contracts the remaining electrons closer to the nucleus. So cations are actually shrink in size. Anions, like compared to the parent, this is the rule of thumb you should know from Chem 1A. Does anybody remember the rule of thumb regarding size? It's a rule, it's not a law. But regarding size, the size of a cation is how many times smaller than its parent atom. So if you take a sodium atom, 100 picometers roughly diameter, the size of the cation is about 50. Good. So it's about half the size. And for anions, they're about how many times bigger than their parent? 2 times bigger. Good. So if you take something like fluorine and make fluoride, it doubles in size. Fluorine's like 90 something, I think. Anyway, what we have is we have an ionic lattice. And when we have ions like this, they try to pack together to maximize the positive and negative attractions, right? But what that creates is a structure that has little spaces in between. These little spaces are called what? These little spaces between the ions. They're going to be little spaces. Some of these spaces can be taken up by like cations, like this, the space in between here, but then there's going to be spaces in between, like here or here. So like this space was taken up by the cation here, but there are other spaces in here that might not be taken up by the cation, and those spaces are called, these void spaces. What are the void spaces called? Like these little empty spaces between the balls. We give them names: octahedral, tetrahedral, cubic. Remember we call them what? You see, this is, I notice a lot of people maybe they are studying for med, and then when you take the MCAT, are you going to forget everything and then have to redo? I mean, can you redo 2 years of chem? How long is it going to take to redo it? And so if you're planning to take the MCAT, what you need to do is you need to start reviewing like now. And then that way you don't forget it. Because if you forget everything and you come to take the MCAT and they have some structural problem like this where they're asking you about octahedral hole in a sodium chloride lattice or something like that, what's inside the octahedral hole? The sodium ions are inside the octahedral hole in a chloride lattice. Not that that would be a question, but that was a question on a standardized test I took when I was a student. It was talking about the holes. The octahedral holes and tetrahedral holes. I remember it vividly because they had really nice drawings, and I thought, wow, those are really nice drawings of the crystal lattice, But anyway, if you're planning to do something like this, like medical, and that's your goal, and I know a lot of people that's their goal, then what you need to do is you need to start, so you don't forget everything. I know somebody who's planning to take 2 years of gap to review everything because they've forgotten everything. And then they're going to take the MCAT. But, you're supposed to take the MCAT while you're in I guess undergrad or something. I don't know. The medical school admissions is so complex. But the same thing happened to my friend. My friend asked me to help him prepare for the MCAT test. And that's fine. My friend was a bio major. I was a chem major. This was at UCLA when I was a chemist. And he was, I think this was our last year there, or second to last year there. And so I sat down with him to review chem because he was preparing to take the MCAT. He forgot everything. Everything. And I mean everything. So what he ended up doing was he ended up taking 4 gap years that he did. He worked, different jobs, but he had to review everything. I couldn't help him because it was too much. Too much. It was like starting from fresh. Like I had to teach him the entire class. So it was that was a wake-up call for me because I mean if you don't use it, you're going to lose it, right? And so he lost it. Didn't really do. Of course, there was some stuff he remembered, the stuff that was applicable for his major, proteins, protein folding, this kind of stuff. But the general chem stuff, it was all gone. He eventually made it in. I mean, it took him a lot of tries, but he got in. He ended up going to the Caribbean, though, the American Medical School in the Caribbean, and actually lost contact with him. But anyway. So you have these little holes here, and what can happen is water can wiggle its way inside and form hydrates. So we end up with hydrates like this, and it depends, how many waters we can fit in. So we'll just write in like NH2O, depending on how many waters wiggle their way in, and it's a solid, into these holes. Well, the same thing. People thought, okay, water is very polar. Ammonia is very polar. Both of these can hydrogen bond. And so ammonia can also wiggle its way in and form not a hydrate, but an analogous compound as a hydrate. It's just the ammonia molecules get stuck in there. Ammonia is already a gas. It's no problem. And the ammonia molecules get stuck into these little holes, and we form this. And so going back to this compound here, the way this used to be written, do you see there are 3 ammonias here? The way this used to be written before Werner was it would be written like this, COCl3, and the amount of ammonias depends on how many holes we have, vacancies we have, and how many we can fit in. Maybe we could fit in up to 6, we can squeeze 6 ammonias in there per formula unit, then this would be it. Therefore, when this dissolves in water, what happens to ionic compounds if they're soluble? If they're soluble, what happens? They break apart into ions. They ionize in solution. Now, cobalt 3+, this is a powerful oxidizer, so we have to be careful. And then this lattice is expected to be strong. So I'm going to put a little asterisk here. Plus 3 chlorides, plus 3 ammonias. So we expect it to just break apart the ionic lattice, and we end up with these aqueous species. You could easily test this with silver nitrate. If we add silver nitrate, what's going to happen? What will the silver nitrate react with? Chloride, right? And it's going to precipitate out what? Silver chloride. So we should expect 3 silver chlorides to precipitate. This is what was expected. However, that's not what was observed. What was actually observed was not 3 silver chlorides. What was actually observed was only 2 silver chlorides. So, oops, what am I doing? This is an S here with parentheses, not 3. 2 silver chlorides precipitate. So what you do is that must be a mistake. So you redo it over and over and over again. And so this is reproducible. Whatever you do, this in science, results have to be reproducible. The way we reproduce results is people repeat the experiment. The way people repeat the experiment is they're going to be repeating the experiment based on your observations. So typically when you record observations, you want to record enough observations so that somebody else can repeat the experiment exactly in the same way that you did it and get exactly the same results. So when we take observations, we need to make sure that they're reproducible. And so this is reproducible. And so what that means is that our current understanding of the structure of this was incorrect. And so eventually Werner did this and came up with a new hypothesis for structure. This new hypothesis was that we formed these coordination complexes. And this hypothesis gained widespread acceptance. When a hypothesis gains widespread acceptance, it becomes a theory. And so this is Werner's theory of coordination complexes, basically. And we have the structure wrong. The structure is CONH3. What was it? NH3. Let me take a look. 3. I guess this was only, what is it? CL. I don't know where I got this. This is not the same one Werner did. I think they did chromium complex. Cl2. And so this is coordinately covalently bound. This is usually cobalt-3 forms 6 coordinates, so I don't know why this 3. I just copied this from somewhere. These are ionically bound. And so if this is 4 coordinate, then we have a choice. The 4 coordinate could be square planar or it could be tetrahedral. That we usually determine. There are certain ways of determining it. So we got, let's see, one of these, we got 3 NH3s. And then we have these chlorides out here. Recall that we don't show ionic bonds with a line. We just show ionic bonds with adjacent charges, like that. And so this would be the structure of this. And so when you dissolve this in water, the lattice breaks apart, but these big cations here stay intact. And that would be the triamine chloro cobalt 3 ion cation. Okay. So that was based on Werner. No, question number 7 is supposed to be based on Werner. Section 24.1. What is the I didn't talk about it much though. What is the coordination number for this? Dichloro bisethylene diamine platinum 2. 6. Which is expected to be the strongest ligand? Strongest ligand should be the most reactive. Out of those, which one's the most reactive? B is correct. B. I mean, yeah, B's going to kill you, right? Carbon monoxide. Will chloride kill you? A little bit of ammonia kill you? A lot of ammonia will kill you for sure. But, you know, a little bit of carbon monoxide, you know what the allowable limit of carbon monoxide is? A part per billion level. You know, we can't exceed like 10 parts per billion for an 8-hour period, carbon monoxide or something like that. It's really low. That's because higher levels will end up killing you. Well, water can kill you. Unfortunately, they had like this water drinking contest in the San Joaquin Valley, and the person who won it actually ended up dying from. You heard of that on the radio? Yeah, that was pretty sad. It's sponsored. I don't think they're going to have any more of those contests. Hydroxide, yeah, that could kill you. I mean, high pH, but you know, a little bit of hydroxide. People drink this. People like alkaline water. Alkaline is hydroxide, right? And some people drink pretty high pH, like pH 8, pH 9. You know, it tastes slippery. So, the carbon monoxide is nasty. What makes carbon monoxide so nasty? Well, we talked about this. Remember, carbon monoxide has a very unusual Lewis structure, where the oxygen is actually positive and the carbon's negative. Negative, what color does negative get in the electrostatic potential map? Unfortunately, red. Makes it quite basic. And the oxygen is not so basic because the oxygen is quite positive. This is going to get blue. It's a great ligand, carbon monoxide. Or the carbonyl ligand. Carbonyl ligand. B. 10. What's the correct answer for 10? B. Diamine silver 1 ions, correct. 11. A. Okay, this is the way I did this for myself. We have gold here, but it's an anion complex, so we have to call it goldate or orate. Orate. So that automatically eliminates C and D and E. So it's between A and B. So when I look at A and B, the difference is in the charge on the gold. So what is the charge on gold? Got to be. It's got to be 3 because we have 4 chloride O's or 4 chloros. Uh-huh.
Are we supposed to put ion at the end of the answer?
Are you supposed to put ion? No. Unless it's unclear. If it's unclear, you must use the word ion. So if somebody says, you know, what was your sodium intake today? You know, that's unclear. Because are they asking, did you eat any sodium metal? If you ate sodium metal, your tongue would catch on fire, basically. And they must be talking about sodium ion, but it's totally unclear because sodium is used for both the metal and the ion. The metal's terribly reactive. It's a powerful reducing agent, and the ion is, sodium ion is one of the worst oxidizing agents on the chart. It's extremely, extremely weak on the redox chart. So in that case, you must use ion. Like if I said sodium and you just, you know, or sodium ion, it makes a huge difference. But here, this has got to be an ion. If you add up all the charges, it comes out a net charge. And so in a case like this, we don't need. So if I say carbonate, I don't have to say carbonate ion each time. I say carbonate. Everybody knows carbonate is not neutral. Everybody knows carbonate has a 2- charge. So there are cases where you do need it and cases where you don't need it. Yeah. This is a case where you don't need it. So if I don't need it, I'm not going to write it there unless I want to emphasize that it's an ion. Number 12. What did you? E. Yeah. Well, the first one is it's you know the metal is at the end, so the ligands come first. So that's CDE. And it's a cation. Cations are written first, so we can eliminate C because that would only be for an anion, cuprate. And so it's between D and E. Tetramine, copper 2. Okay, both of those are fine. Okay, then we have to go to the anion. And so we're going to have tetracyano diaquaferrate 2 or diaqua tetracyanidoferrate. So this is, the ligands are named alphabetically, so it should be diaqua cyanidoferrate 2.
I feel like you should give me that point back because I picked C because you told me right before that we have to use the old name, so I didn't look at your E.
No,
I said copper.
I didn't. I never said we have to use the old name. I said you can use the old name or the new name. It doesn't matter. But I would have never said you.
That's not true.
No.
No, yesterday right before the test.
No,
I was like, do you have to use the old name or is that
No. I said you.
have to?
I didn't. I've never
No, you
said
you have to, like word for word. That's what you said.
you have to use the old name.
Yeah, because I said, do you prefer it? And you said, no, you have to.
But
So I eliminated D and E right away.
no. I never said you have to use the old name.
Does anyone else remember that?
Then I must have misunderstood either that or it's very weird because I don't know. How many times did I say I don't care which one? Does anybody remember me saying that like multiple times? I don't care which one you use?
Yeah.
You don't remember that, Tristan? At all? Yeah, I've said it many times. I don't care if you use cyano or cyanido, and I gave examples of that. I said cyano or cyanido is fine.
Copper, the old name. In the first one. Copper 2 for cuprate.
Oh, which one did you choose? C?
I chose C because I didn't think you could use copper.
Isn't C wrong because it's not enough?
The C is wrong
Well,
because.
I see it's not in alphabetical
Oh,
order.
okay. You're saying about the metal. I said, okay. Then now maybe I understand what you're saying. You have to use the old name for anions. If it has a net charge, you must use the old name for only certain ones. So, for example, cobalt is you don't use the old name. I call it a Latin name. For like cobalt, you call it cobaltate. But for the ones like Fe, ferrium or Cu, cuprium, or Sn, stanium, you have to use the Latin name for the anion, not the cation.
You didn't make that clear.
No. I assumed. Wait. Well, anyway, I could talk to you after class more about this, but I assumed you're talking about the anion. The cation, you never change the name. The cation is always the same name. And so there's a disconnect there. But let's talk about it later because I think most people recognize for cation complexes, you leave the name alone of the metal. For anion complexes, you change the ending to 8. And then if it's one of these ones with a weird symbol, then you use the Latin name. Otherwise, you just use its normal name, and that goes. What's the old name for manganese? Is there an old name and a new name for manganese? Then what would you do if I said use the old name for manganese?
Yeah, but if it has an old name, I'm going to use the old name.
All right. Well, anyway, there's another problem. So, I'd like to give it to you, but then you're missing another important rule. And another important rule that you should have known is that cations, you don't change the name. Cations, you have to use the original name. And regardless, if you're going to use the old name, then I put that in the context of anion complexes only. And so I don't necessarily agree with that,
All right, give me another one. I'll get it right this time.
Okay. But anyway, we'll have other ones. This is it. This is 24 points. We're going to have a lot more points. All right. Any other questions on this? All right, we're going to move into chapter 17 today, but let me talk about chapter 16. So chapter 16, the important thing is we want to know what K is.
Oh, you're talking about it.
And so the ways we can determine K is experimental, by measuring the equilibrium values. Measuring means having to do a lot of work. And so we can calculate K using relationships. And these are Hess's law style relationships, but it doesn't follow Hess's law. You know, Hess's law we add using Hess's law type relationships. In these relationships, we end up multiplying rather than adding, and we end up raising things to a power. When Hess's law would have had us multiply. And so we can calculate K. Later on, we'll see we can determine K using thermodynamics, using theory. So we're doing the experimental approach here, the observational approach. So this is K determined empirically from observation. But we can also calculate K from theory, thermodynamics. This is going to come later. And so some of the homework problems involve determining K from equilibrium or from initial. You know, we might have initial and then we figure out the equilibrium or something like that. All right, then what we want to do is we want to use this for stoichiometry. So the next thing is using K to determine equilibrium concentrations or equilibrium pressures. And there we use the ice table. This is using K. The next thing we looked at was Le Chatelier's principle, and this is the lab yesterday. We looked at this qualitatively. This way or this way. Also, I forgot to mention one other thing here. When we do the ice table, we like to know the Q value. So sometimes we calculate the Q. Do you remember the Q value? Q is the initials. So Q is a preliminary check to see if it's already at equilibrium. Because if the initial values give us a ratio that's equal to K, then it's at equilibrium. So if Q equals K, then we don't really need to do anything. It's already at equilibrium. The case where we have to use the ice table is when Q is less than K, there's not enough product. So we need to shift to the right. Or if Q is greater than K, there's too much product. We need to shift it back to the left when it's not at equilibrium. So the ice table, we can see which direction the change is going to be. Is the change going to be from left to right or right to left? Sometimes it's easy to see, you know. Okay, the other way we could do Le Chatelier's is quantitative. And so I want to do a calculation where we do Le Chatelier's quantitatively. save this. And so I'll just grab a problem from the book. There's some, this is a good section too. This last section of chapter 16, which goes through representative calculations. You should take a look at those calculations and make sure you can do them all. 16.7, equilibrium calculations, some illustrative examples here. All right. And then some homework problems. This is just like Hess's law style problems where you just add up the reactions and figure out what the K for the net reaction is. Determination of equilibrium constants. Here they're going to give you at least one equilibrium value, and then you might have to figure out the others using just stoichiometry. Once you get all the equilibrium values, you just plug it into the K equation, and then you can determine it. Figuring out the K equation comes earlier here, you know, in the homework. They just ask you to determine the K expression. Expression would be, you know, the products. What are the products? What are they raised to? Over the reactants. What are the reactants and what are they raised to? This is the K expression. Here we have Kc and Kp. I gave you the equation for that, determining that. Here we have a K. Is this favoring the product or reactants, this particular K? This one's favoring the products, 9,000 here. Is H2O liquid, what's the activity of H2O liquid? 1, right. And so in this K expression, H2O liquid is just 1. We don't even write it there. So it's just the concentration of iron divided by the concentration. This is a problem. Is this iron 3 hydroxide a solid, liquid, or aqueous? This is a typo in the book. This would be this has to be a solid. Okay. This is an acid-base reaction, Bronsted. This is a weak base, iron 3 hydroxide, even though it has 3 hydroxides. And the reason it's a weak base is not because it doesn't have a lot of hydroxide. The reason it's a weak base is because it's, yeah, Rebecca?
Oh, I was gonna ask, like, for the K value, like, whenever it's, like, big values, if there's products, and like, when it's small, there's
Right, right. The K values span huge orders of magnitude. You know. And so oftentimes, when something spans huge orders of magnitude, like earthquakes, you know, earthquakes span huge orders of magnitude, so they have the Richter scale. The Richter scale goes by powers of 10. Whenever you have something that goes over many, many orders of magnitude, we like to use power functions. The reason why we like to use power functions is because it's easier. So this would be like 10 to the third. This is almost 10 to the fourth. And so this is getting close to 4. Or wait, 2. What is this? That would be 10 times 10 to the third, which would be 1 times 10 to the fourth. Yeah, it's between 3 and 4, so let's say. If we're looking at power functions. And so we have things called pKa's. So a lot of tables, rather than writing things in scientific notation, they convert them into power functions, which saves space. Like pH. pH spans many, many orders of magnitude. So if I see a pH 7, that's a power function. Power function, and this is actually a negative power function. So if I see pH 7, then the power is 10 to the negative 7. That's the power. If I see a pH of 6, then the power is 10 to the negative 6. Power function of 10 to the power function of pH of 2 is 10 to the negative 2, you know, etc. And so power functions are very useful, and we use power functions exclusively for pH, the power of the hydrogen ion concentration. That's the pH. But we can also use it for anything. The power of the K, pK, is very common. We'll be looking at pK's values too. This is, we expect, when we see something like 57.5, expect significant quantities of both, the gas and the dissolved ammonia in solution. Here, Kc of 281, significant quantities of both. This is a redox reaction. Sulfur dioxide, sulfur is in the +4 oxidation state, being oxidized to sulfur in the +6 oxidation state. And so here at the 1000 Kelvin, we expect both. At 1200 C, this 10 to the -2, this favors. It's difficult too because here this is second order in the numerator, here it's first order in the denominator. So we have to keep that in mind too when we're looking at which side's favored, because that makes it more tricky when it's nonlinear like that. And so this appears to be favoring the reactant, I suspect. Here we have this. I mean, this is huge. This is 10 to the 19. That's big. And 10 to the 19 means this heavily favors the product here. Sometimes we write these as fractions. You see these as fractions when we want to normalize it per mole of ammonia. Per mole of ammonia, how much do I need of everything else? And so fractions are common. Looking at that. These are Kp values. Kp values, well, these are all gases, so it makes sense. We could also use Kc. Kp and Kc are the same if the number of moles of gas are equivalent on both sides. So when I look at this, the number of moles of gas are inequivalent, and therefore Kp and Kc are different. Same thing here. I have 1 mole of gas here. I have 1.5 moles of gas here on the side. If I had 1 mole and 1 mole, or 1.5 moles and 1.5 moles, then Kp and Kc are the same. This is because the RT term drops out. Sometimes we look at mole fractions. You know, mole fraction would be the number of moles of C2H2 over the total number of moles. C2H2 is acetylene, is its common name, etc. And so just some case. I just kind of scanned the problems, see what types of problems are asked here. This is a more conceptual question here. Here we're looking at a direction. Direction is Q. You know, Q, what direction is it going to go? 3 choices there. And extent. Extent is ice table. And so we can do some calculations here. So just more, these are just ice calculations. We set up the ice table, initial, change, equilibrium, and then go from there. Some conceptual problems. Sometimes there are a lot of oxidizing agents and reducing agents, you know, that aren't on the chart. You know, so sometimes like the oxidized form and the reduced form, NAD. Sometimes we write this as NADH. Usually H represents a reducer, and O represents an oxidizer. That kind of makes sense because hydrogen's a really good reducer, O is a good oxidizer. So, Yeah, we are. We're gonna go through it. I'm just kind of going through some of this. So, but we'll talk more about this as we go along here. About in just a minute. I'm almost there. So here, this is a redox reaction, but NAD is the formula for that's kind of long, and so it's easier to abbreviate it. And then the oxidized form or the reduced form is usually NAD, and an NADH or something like that. This one, they wrote OX and RED to talk about it. And so what they're doing is it looks like they're reducing or oxidizing something here. Citrate, and oxoglutarate. These are ice tables using KPs. Same thing, except we're dealing with pressures. So P initial, followed by some change, which I could call X, and then P equilibrium. And then we have Le Chatelier's principle. Le Chatelier's principle, a lot of these are just qualitative. Here. Reactions with very small or very large K values. And so I'm going to talk about some tricks. Something you need to know in math or in science is how many digits does your calculator carry in a calculation? Does your calculator carry an infinite number of sig figs? Is that even possible? No. So how many sig figs can your calculator carry max? Anybody know? I know how many digits my calculator carries. My calculator carries 10 digits. Excel, do you know Excel? How many digits Excel carries in a calculation? Last time I checked Excel, it carries 100 digits. 100 digits is a lot of digits, right? But what happens if I exceed that number of digits? What will the calculator do? Will the calculator crash if I exceed the number of digits? No, it doesn't crash. But what happens is the calculator rounds the number. If your calculator rounds the number, then you have a potential problem. And this problem comes up when we have just scroll. What happened to this? Scroll back. So these are all qualitative Le Chatelier's. I want to do quantitative calculation for this. But before I do that, let's take a look at this here. So the equilibrium constant for the following reaction is 10 to the minus 16, which is very, what? Very small. At 25 degrees C. What is the concentration of copper 2 plus when excess CuS reaches equilibrium with a solution in which the hydronium is 0.30 molar and the H2S is 0.10 molar? So equilibrium with a solution, when excess CuS reaches equilibrium with a solution in which H3O plus is. Okay, this is something we have to think about in all these problems. When we're dealing with ice, and we deal with ice all the time for these, are these equilibrium or initial? So read the question and tell me, are those the equilibrium or the initial values? Equilibrium, would you say? Okay, if it's equilibrium, then this is super easy problem. We don't even have to do an ice table because they're already telling us what the equilibrium values are. And so if this were equilibrium, let's take a look at what I would do for this particular. What happened to my problem? Just keep scrolling. All right, so this is number 71. So K is equal to Okay, we're going to get KEQ. KEQ represents things in terms of the activities, and so the activity copper 2 plus is going to be close to its molar concentration. Let's raise. And then H2S aqueous, we'll plug that in here. This is going to be H2S aqueous. And then CUS, what's the activity of CUS, solid? It's 1, so I'm not even going to write 1 here. And then hydronium is going to be squared here. So if this were at equilibrium, you know, all these are going to be at equilibrium, E, then we have everything here. So we go 6 times 10 to the minus 16, which is our K, and then all we have is one unknown, Cu2 plus. And the H2S is 0.10. Activities are dimensionless, so I don't write M for molar. And then 0.30 squared. And so we're using the concentration for activities, but activities are dimensionless. So this turns out to be a super easy algebra problem. But some of these can be very difficult to do. Let me give you an example of something that's very difficult to do here when we have a very small or very large value. We'll just use one of these reactions, but let me put in the conditions here. We're going to use this reaction here, but number 71, but we're going to do it differently. Oh, actually, no, this one's fine. Let me do a big one. Let's do number 74. We have, when we're dealing with strong acids and strong bases, we have 2 ways that we approach it for strong acids and strong bases. Actually, let me show you here. So we have the strong acids here, the 7 common strong acids. Well, I don't know why the resolution's so bad. Anyway, perchloric, hydroidic, etc. And we have a Ka value for these. This is how we're going to get a gauge of the acid strength. And so when we're looking at acids, actually, like this, this is going to be a side. This is not related to the problem, but I'm going to do this anyway. What we say is that strong acids are strong electrolytes. Strong electrolytes do what? Dissociate or hydrolyze completely. And so if I have a strong acid, let's take a strong acid like, which one? HCl? That's a strong acid. It dissociates or hydrolyzes completely. So this is kind of one way here. And so we got H plus and chloride like that. That's dissociation. Hydrolysis means what? Yeah, it breaks apart water. Hydro, water, lysis, break water. And this is going to form what? Yeah, H3O. Charge on H3O? Plus. And hydroxide? Not hydroxide. H3O plus and chloride. Both of these are Ka. So one way I can represent the Ka here is this is going to be the H plus concentration over the chloride concentration divided by the HCl concentration. Or I can write it down here. The Ka is going to be the hydronium ion concentration times the chloride ion concentration divided by the HCl concentration. Both of these are the same. These are equivalent. If this was 100% ionization or hydrolysis, then what's the equilibrium concentration of HCl? How much HCl do we have left over unhydrolyzed or unionized? We'd expect to have 0. You know, if it's 100%, there's nothing left, correct? And therefore, K should be what? If the HCl concentration in equilibrium is 0, then K should be infinite. That's what it should be. So K, we expect it to be infinite if it's truly 100%. So we go over to this chart here and we take a look at the Ka value. Take a look at the Ka value for HCl. What does it say? Or HClO4. You look at the Ka value for HClO4, it's over there on the far right. It says very large. So maybe what they're talking is very large. It's close to infinite or something like that, right? And so what we just assume is we assume complete reaction. It might, but they don't say infinite. They should say infinite, right? Or approaching infinity. They don't say that. Do you know it's not really infinite? It's not really infinite. It's just a very big number. This is a very big number. It's so big that, you know, the amount of unreacted HCl is minuscule. You can't even really measure it, you know, unless you have a huge ocean of it. Then maybe you can measure it. And so what they say is that we just assume complete reaction. So here we just write a one-way arrow. In reality, it's a two-way arrow, but here we're just going to write one way. We assume complete reaction. Assume complete reaction. I mean, how can we do a calculation? Complete reaction. We can't do a calculation because there's no very big key on your calculator. Is there a very big key on the calculator? No. And so assume complete reaction, 100%. All right, that's fine. Now, the strong bases are the same. We have Kb for bases. So let's do chloride. You know, the chloride's a base. Do you see it up there? I see chloride up there. Actually, I'll just show you on this chart here. Do you see chloride here? It's on the base side. This is what we call the conjugate base of HCl. So HCl is the acid, its conjugate base is chloride, or chloride's the base, its conjugate acid is HCl. So these are conjugate pairs. And so we have chloride there. How does chloride, you know, chloride's a weak base. Do you know the conjugate relationship? If one side's strong, the other side is weak. And so chloride's a weak base. So chloride being a weak bases do what? Weak bases partially hydrolyze in water. Do weak bases partially ionize? Well, how are you going to ionize chloride? Can you tell me what it ionizes into? No, it doesn't ionize. Chloride doesn't ionize. And so that's one important difference here. And so chloride, the only thing it can do is hydrolyze water like this. And what's going to form is what? This is a proton transfer reaction. So we transfer a proton, and we're going to get HCl and hydroxide. Already, this doesn't look like a great reaction, does it? You know, you could look at this and say it's not going to be very good because, one, this is our base, this is our acid, going forward. And going backwards, which one's losing the hydrogen? Going backwards, this is our acid, this is our base here. Are we going from stronger to weaker or weaker to stronger? We're going from weaker to stronger. This is going to be heavily favored in the reverse. So if any reaction occurs here, it should be very small because there's a huge difference in base strength. You know, chloride as a base versus hydroxide. And this is where you need a little bit of observation, that is memorization, in theory for this. And so you need to know, well, chloride is a base, but how good of a base is it? It's an awful base. It's so bad that we don't really consider chloride to be very basic at all. We consider it to be neutral. But that's base hydrolysis. So I want to make one point here. Acids produce hydronium. When we produce hydronium, what that does is it increases the hydronium concentration, and pH is flipped. So if the hydronium ion concentration increases, the pH decreases because it's flipped. It's got a negative inverse relationship. And bases produce hydroxide in solution. And so pH is the power of the hydrogen ion concentration. There's something called pOH. pOH is the power of the hydroxide concentration. And so, as the hydroxide ion concentration goes up, the pOH goes down, and vice versa. This is not going to produce much hydroxide in solution at all. This is extremely weak. And there's a conjugate relationships, Ka and Kb, for conjugate pairs. The way it's going to work is a seesaw type relationship. It turns out that Ka for HCl times Kb for Cl minus is equal to something called Kw, which is a constant. So if this one's very big, then that means Kb for chloride must be very small. Ammonia is an interesting compound. Do you know ammonia can go either Ka or it could go Kb? If ammonia goes Ka, then ammonia is acting as an acid or a base? Ammonia is acting as an acid. And so when we do Ka, that's acid plus water. When we do Kb, that's base plus water. So ammonia plus water, and ammonia is acting as the acid, what forms? What forms is NH2 minus. And hydronium. Is ammonia a very good acid? Is ammonia a very good acid? Let's take a look at where ammonia is. Is ammonia a very good acid? No. It's one of the worst acids on the table. And its conjugate base is NH2 minus. Therefore, if NH3 has a very small Ka, then the Kb for NH2 minus must be very large. Means very large Kb. And therefore, do you know what NH2 minus is called? NH2 minus is called amide or amide, and it's a powerful base. So when I have my students memorize the strong bases, these are the strong bases here. The strong bases are the soluble sulfides, the soluble amides, the soluble oxides, the soluble hydrides, and the methide. Methide is the strongest base on this particular chart. It's very unusual. When you look at methide, you know, carbon likes to form 4 bonds. There's only 3 bonds here and 1 lone pair on it, making it a powerful base here. All these Kas are extremely small, therefore all these Kbs are extremely large. And strong bases do what? Strong bases ionize completely or they hydrolyze completely. I mean, what does amide ionize into? I've given this problem many times, and people ionize it. They try to break it up in nitrogens and hydrogens, so they get like nitrogen and a hydrogen, or, you know, 1 nitrogen, 2 hydrogens, and so they try to break it up. Same thing, if I put on methide, they try to ionize it. It doesn't ionize. And so that's why I'm emphasizing that point. So normally what we say is that if I had amide, we just say it's going to react to completion. Here, there's barely any reaction. I mean, this is hugely uphill. This is going to be heavily favored downhill because the Ka is so very small. Whereas if I had amide and I'm looking at the Kb for the conjugate, amide plus water is going to yield what? Ammonia plus hydroxide. And it being a strong bases ionize, or I shouldn't say ionize, strong bases hydrolyze completely. And so what we do is we just assume 100% reaction here. We assume 100% reaction because we aren't going to do any calculation, 100% reaction. Because Kb is very large. Kb is very large, and there's no very large key on your calculator, so we don't do a calculation for this. We just assume it's 100%. For strong. Strong bases produce a lot of hydroxide. Strong acids produce a lot of hydronium. This is the difference between the acids, hydronium and hydroxide. So let's take a look at this problem here. The equilibrium constant for the following reaction has been estimated. So, you know, very large should be infinite, right? Because there should be 0 reactant left over. If you have 100% reaction, there's nothing left over, and you get a 0 in the denominator, it should be infinite. Is that anywhere close to infinity? No. In reality, it's not. But when you're at 10 to the 20th, it's almost as if it's infinity because there's such a small population that's left over. It's easy to miss them. You know, it's like being out in the desert. And the population of tropical trees is probably 0. But anyway, at 25 degrees C, estimate the equilibrium concentration of amide in a solution prepared by dissolving 0.0125 moles of sodium amide in water to make 1.00 liters of solution at 25 degrees C. Is the result physically meaningful? All right, so this is a case where there are certain tricks to make your life a little bit easier. And we'll talk about those tricks, depending on your calculator. And so the first trick I'm going to talk to you about is resetting the initial conditions. Oh, shoot. How does this go back? What was it, 0.0125, I think. Pretty sure it was 0.0125. I'm not going to scroll back. It's running out of time. How much time do we have? 5 minutes? All right. So the reaction is this. Amide plus water yields ammonia plus hydroxide. And we're going to treat this as equilibrium because now we have a K value. The K value is estimated to be roughly 10 to the 20th. So the power would be 20. Quite high. And then it's 0.0125 per liter, I think. And so the initial is going to be 0.0125 molar. Now, do you know the concentration of water? The concentration of water in pure water is 55.5 molar. But it doesn't change. Does the activity of water change? So when we have water in the ice table, we just draw a line. We're not going to deal with it because it's a pure liquid. And then we're going to go 0 molar and 0 molar. So which direction is this going to go? Do I have to calculate Q? No, I don't, because it's only one way it can go, and that is minus, plus, plus. In other words, this cannot be plus, minus, minus, because we can't go lower than 0. 0 would be the floor. And so at the end of this, at equilibrium, we're going to have 0.0125 minus x. This is an x and x molar. Now it's important to use concentrations here. I cannot use moles here. I can't use moles here. It just doesn't work. It has to be molarity. I could use moles here if the units would cancel out, but they won't cancel out. Like I'll have molar squared on the top, molar on the bottom. And so they don't cancel out. If I had molar squared on the top and molar squared on the bottom, then I could use moles. It wouldn't matter. All right, so now we just figure out what K is. K is going to equal the concentration of the products, ammonia, raised to the first, times the hydroxide, raised to the first, divided by the concentration of the amide, raised to the first. And then water is just an activity of 1. And so what we need to do is we have K here, 10 to the 20th. This is going to equal K down here. And so this is going to equal X times X divided by 0.0125 minus X here. And so this is just quadratic. And so I'm going to get this into quadratic form here. And so getting this into quadratic form, I'm going to do 0.0125 times 10 to the 20th. So this is going to be 0.0125 times 10 to the 20th. Okay, minus 10 to the 20th x is equal to x squared. And so then I'm just going to get this into complete quadratic form. This is x squared plus 10 to the 20th x minus, okay, I'm going to change this. I'm going to call this 1.25. I'm going to move the decimal over. So if I move the decimal over 2 to the right, so I'm making this bigger, I've got to make the coefficients smaller in scientific notation. This is continuing to scroll. It's quite annoying. So I'm going to call this 1.25 times 10 to the 22. Is that right? Make this 10 to the 18. So minus, don't scroll again. Minus 1.25 times 10 to the 18. Is that correct? E is equal to 0. All right, then I have my handy calculator, which does the quadratic. But if I'm doing homework, then I'll just do this. I'm just going to go to online quadratic solver. So just go to quadratic formula calculator. I'll just pick the first one. And so A, I'm going to call, what is A? 1. So A is 1. B is negative 1 times 10 to the 20th. Is that right? C is what? C is, oh no, positive. C is 1.25 times 10 to the 18 negative. Negative 1.25 times 10 to the 18. So for these calculators, we use E for scientific notation and then calculate. So my answer comes, I get two answers. X is equal to 0 or X is equal to negative 1 times 10 to the 20th. And so the two roots for this, X is equal to 0 or X is equal to negative 1 times 10 to the 20th. So which one is it? Actually, there's an error. I must have made a sign error here. But I'm out of time, so we'll complete this next time. My answers don't make sense.